So let's look at an application of a rational function, an example maybe where this might be used, these rational functions might be used in a real world type scenario. And one of the best examples that I can think of is an average cost function. Okay, so in the business world, let's say that you own some kind of manufacturing company and you are going to have to, you want to make a profit, but you're going to have to weigh out how much your expenses are in order to figure out how much you should charge for your items that you're selling so that you can make a profit. So one thing you're going to probably want to calculate is what we call a cost function. Cost function is how much money you are spending for your business, okay? Cost function, we're going to call that C of x because it is a function, is based on two components, your fixed cost and then your cost per item, your variable cost. And we studied that back in, I think, in chapter 2. So fixed costs would be things like how much rent you're paying for your building, how much you have to pay just for salaries to your staff, how much you pay for electricity, how much you pay for insurance, those kind of fixed costs that are probably the same or about the same every month. Okay, you're going to know what that number is and plug it in. Then you're going to have, that should be a CX right there, not CS. This little C right here will be how much you have to pay per item. So if you're making shoes at your factory, maybe your fixed cost is, $20,000 or whatever it is. But maybe in order to make shoes, maybe you have to spend $5 on raw materials. $5 for the leather and the shoelaces and all the stuff that you have to buy to make a pair of shoes. So $5 times however many items you make, that's going to be your variable cost. Because there might be 1 week or 1 month that you make more than another. So this cost might go up even though your fixed cost for your building and all that might still be the same. Okay? All right. Then average cost is how much you spend on average per item that you produce. So it's all of your cost, your fixed cost plus cost per item, divided by how many items you made. Okay? And we put a little line over the C to show that it's our average cost. In math, when we put the little line on top, that's our way of saying average. Okay? All right, so let me give an example here. Suppose a company manufactures a robotic exoskeleton, so some big fancy robot thing they're making. And they have a fixed monthly cost of $1 million. That's expensive because they're probably, it's expensive to make these robot things. So this $1 million is probably the rent on their warehouse and pays for the salaries of their employees and the insurance on their building and electricity and all those basic types of things. They have to pay that $1 million every month no matter how many items they produce. And then it cost them $5,000 to produce each robotic system. Okay? Now that $5,000 is probably for the metal and the plastic and the shipping materials and all the stuff for every single robot that they make. Every robot that they make, they paid $5,000 up front to get all the materials to make it. Okay, so our cost function is how much money they spend. Well, they spend $1 million up front plus $5,000 times however many robot skeletons they make. Okay? Some people like to reverse those, and you could do that. You could call it 5,000x plus the $1 million. If you'd rather write it that way, that's fine. Doesn't really matter. Okay? That's our C of x. That's their cost function. This is how much money they are spending. Part B, write the average cost function, so C bar of x. In other words, on average, how much are they spending per skeleton they make, per robot they make? Well, that's going to be the 5,000x plus the $1 million they already spent up front. Okay, that's the total amount of money they're spending, divided by however many they made. Okay? That's their average cost. All right, keep that in the back of your mind. We know that formula. I'm going to write it up here at the top. 5,000x plus $1 million divided by x. Okay. Find and interpret C bar of 1,000 and then C bar of 10,000 and 100,000. Okay, So remember, every time we put this number in parentheses, they're telling you to plug that number in for x in the original equation. So if they told us to find c of 2, we would be putting 2 in for x. Okay? All right, so they're telling us to put in 1,000. So 5,000 times 1,000, we're putting in 1,000 for x, plus the million divided by x, and we know x is 1,000. Okay, so I'm going to grab my calculator and I'm going to type that in. 5,000 times 1,000 plus a million. So their total expenses to make this 1,000 items was, $6 million divided by the 1,000, and we get 6,000. Okay, that means if they make 1,000 robots, it will cost them an average of $6,000 per robot. Okay? All right, let's find the next one, and then we'll make a little comparison here. We'll talk more about what that means. Okay, so C of 10,000 means take this equation and put in 10,000 for x. So 5,000 times 10,000 plus a million divided by 10,000. So there's my top part, divided by the 10,000 on the bottom. And oops, I have a typo in there somewhere. Let's see here. Oh, because I put 1,000 instead of 10,000. Let's try that again. What am I doing? Yeah, 5,000 times 10,000 plus the million, and then we divide by our 10,000. Had a typo there a while ago. Okay, it's 5,100. Okay, so that means if they make 10,000 robots, it will cost them an average of $5,100 per robot. Okay, well, why did it go down? Why is it only costing $5,100 instead of $6,000? Well, the reason, remember, it costs $5,000 for the raw materials. So if they're buying the plastic and the metal and all the parts to put together the robot, that's always $5,000. Every single robot costs them $5,000 to make. But remember that upfront cost of $1 million? They pay that $1 million for the warehouse and the employees and the insurance and all that. They pay that no matter how many robots they make. So when they made 1,000 robots, that $1 million was getting divided among 1,000 robots. But when they made 10,000 robots, that $1 million was being split among 10,000 robots. So it was less money per robot that they had to spend out of that $1 million. So as they make more and more and more, their average cost will go down. Okay, when they made 1,000, it was costing them $6,000, $5,000 for the materials, and the extra $1,000 was for the share per robot of that $1 million. When they made 10,000, it was still $5,000 per robot, but that $1 million for the upfront cost was divided among 10,000 instead of only 1,000. So their overall cost was $5,100. Let's do one more time. They said for 100,000. So if they make 100,000 robots, 5,000 times 100,000 plus the $1 million up front divided by 100,000. Okay? All right, so 5,000 times 100,000 plus the $1 million, that's their total expenses, divided by the 100,000 robots they're making, is $5,010. Notice the cost went down again. If they make, I don't really have room to write this under here, but if they made 100,000 robots, it cost them an average of $5,010 per robot to make each one. Okay? All right, then part D says, what's the horizontal asymptote for the graph? What the heck? What does this have to do with horizontal asymptotes? Well, go back to that C of x function. That C of x function, 5,000x plus 1,000,000 divided by x. This is a rational function, right? We've got an x in the denominator. And to find horizontal asymptotes, remember, we use Bobo, Botan, or Coco. Well, which one is this? This is a Coco because the x's both have exponents of 1. So this is a Coco, and our coefficients are 5,000 over 1. So our horizontal asymptote is y equals 5,000 divided by 1, which is just 5,000. That means our horizontal asymptote is at y equals 5,000. Okay, what does that have to do with the robots? Well, that means as we produce more and more and more robots, the cost will go down. Remember, we went from 1,000 robots, it cost 6,000 a piece. If we made 10,000 robots, it cost $5,100 a piece. If we made 100,000 robots, it cost us $5,010 a piece. So if we made 1,000,000 robots or 10 million robots or a jillion robots, whatever, however many you made, okay, the cost will keep going down, but it's going to level off and approach 5,000. It will never go below 5,000 because that is where the horizontal asymptote is on our graph. My horizontal asymptote would be at $5,000. So my cost will come down. As I make more and more robots, my cost will come down, but it will never go below 5,000. It will approach 5,000. Why 5,000? Because that's how much it was costing us in raw materials. Okay? So if we made, a billion of them or whatever, huge, huge, huge number, it would still cost us $5,000 per robot. Now that $1 million upfront cost is going to be divided among more and more, so it will cost less per robot to add on to the $5,000. But 5,000 will be the kind of imaginary number that we approach but never get close to. So as we make, and I'm describing what it means to the company here. That's my last part here. As we make more and more robots, the cost per robot, that's our average cost, will approach $5,000. It will never go below $5,000, but that's what the cost will approach. That's a really good example of a real-life scenario that uses a rational function. I think your lab has another example, and it's population on like an island, population of insects or something. So use this same idea. You have a rational function, and you'll be able to find the horizontal asymptote, and it will represent something about the population.